All right, today we have 8.4, using exponential functions. All right, so our objectives today are to write exponential functions to model some real-world situations, such as exponential growth and decay, and then we're also going to use some exponential functions to solve problems. All right, so exponential functions, remember those are y equals a times b to the power of x. They're used in business, science, and economics. Okay, they're going to model quantities that consistently increase or decrease by the same percent of their current value. So it's a consistent increase or decrease. All right, then we've got functions in the form of f of x equals a times the quantity 1 plus r to the power of x can be modeled, can model both exponential growth, so it's growth model when our r is greater than 0, or they can model exponential decay. Okay, so it's a decay model when r is less than 0 but greater than -1. So this is when it's that fraction. Okay, so it's less than 0 but greater than -1. So we might write on there. That's when it's the fraction. Okay, we can also have it, we can have y equals a times b to the power of x, or y equals a times the quantity 1 plus r to the power of x. Okay, any of those things. Here's part of the thing though. These are going to be like exponential growth and decay, these functions, but it is where a, so that first term, is the initial amount. Okay, r is our constant percent change, and x is the per time period. All right, so however many there are. Now, the growth factor, or the base of the exponent, is your b, and that equals the 1 plus r. Okay, so all we've done, like if we think about that, and here we have a times b to the power of x, all we've done is we have replaced that with a b here. I guess I shouldn't say we have replaced that with b. We have replaced the b with the quantity 1 plus r. That is our b, which is why this says b is equal to 1 plus r. Okay, that's our base of the exponent, or our growth factor. But think back to when we just talked about numbers with exponents. We had the base, right? If we had 2 to the power of 4, this number is our base. This number here is the exponent. Okay, that's all this is saying here, is that b is, well, let's go back up here. B is the base of the exponent, so it's the growth factor. Whether it's growth or decay, it's still called the growth factor. And then here we've replaced the b with that quantity 1 plus r. So that is still, that 1 plus r is our base, or our growth factor. Okay, let's start with examples then. Example 1 says to write the exponential function of the form y equals a b to the power of x for each situation. Notice we've got a few notes there. We're going to substitute the x and y values of each point into the general form to create a system of equations. Okay, then we're going to solve the system and write the exponential function by substituting the values of a and b into the general form. So first of all, for a, we've got a graph that passes through 212 and 596, those coordinates. So we're going to substitute the x and y values of each point into the general form. So our general form is y equals ab to the power of x. So we're going to take 12 is our y, so we're going to do 12 equals ab to the power of 2. Okay, and we're going to have, for our other one, our y is 96, so we're going to have 96 equals ab to the power of 5. Okay, so first of all, that's all we did, that first step there. Then we're going to solve the system. Well, in that case, we're going to have to solve for one of our variables. So I'm going to solve for a here. Okay, I'm going to divide by b squared. So I'm going to get 12 divided by b squared equals a. Okay, once I have this, I've solved for one of my variables. I'm going to put it in my equation over here. So now I've got 96 equals A, which is 12 over B squared. So 12 divided by B squared times B to the 5th. All right, well, we've been working with these exponents, and we know that this is essentially division. And when we have division of exponents, right, they have the same base, we can subtract them. So 5 minus 3 is going to give, or 5 minus 2 is going to give me 3, and this would just be gone. Okay, so our B would cancel out totally. So this would be 96 equals 12B to the 3rd. Okay, then I can divide by 12. And I get 96 divided by 12 is 8. And then I get B cubed. Okay, the only way to get rid of B cubed is to cube root it. So I'm going to do the cube root there. And so now I have the cube root. I have to come over here a little bit. So the cube root of 8 equals B. Well, do you know the cube root of 8? So again, if you take it, we go back to what we had been talking about, do some prime factorization. Like 8 divided by 2 is 4, divided by 2 is 2. So we would have the cube root of 2 cubed equals B. The cube root and the cube cancel, so 2 equals B. Sorry, not B. No, that is right. 2 equals B. All right, that is correct. Then what do we do with it next? Let me erase some of my work here. Yeah, then next we have to bring B back over and put it into the equation here. So 12 equals B squared. B is 2. So 2, or 12 divided by, not 12 equals. 12 divided by 2 squared is going to equal A. Well, that's 12 divided by 4. So 12 divided by 4 is 3. So 3 equals A. That's some terrible handwriting. My goodness. So 3 equals A. There we go. So then it says write the exponential function by substituting the values of A and B into the general form. So my final answer would actually be y. I keep trying to change the color and my board doesn't want to cooperate. Y equals A, so 3 times our B, which is 2, to the x power. Okay, for B then, we're going to do the same thing, but we're going to use the graph. We're going to do it for the graph over here. So we need to pick out some points. So 0, 4 is a great point to use. And 2, 1 is a nice solid intersection we could use. Okay, so we're going to do the same thing. We're going to write those initial equations, those in the general form. So remember that's y equals ab to the power of x. So our y for the first one is 4. So we've got 4 equals ab to the power of 0. And our other equation, our y here is 1. So we're going to have y equals ab to the power of 2 because our x was 2. All right, well, this one's kind of nice. We can go ahead and solve it because 4 equals a. Any number to the power of 0 is 1. So we know that 4 equals a here. All right, so then we're going to plug it in over there. Let's see if I can get my colors to change to track that a little bit better. All right, so 4 is a. So we're going to say 1 equals 4b squared. Okay, we're going to divide by 4 on both sides. So 1/4 equals b squared. We're going to take the square root of that. All right, the square root of 1 is 1. The square root of 4 is 2. And so b equals 1/2. All right, and so our final answer, we're going to take a and b and plug them back in to our general form. So we have y equals a, which is 4, times our b, which is 1/2, to the power of x. So y equals 4 times 1/2 to the power of x. All right. Next up then, let me clear this. Example 2. For each exponential function, we're just going to identify the initial amount. So we're going to rewrite it first of all. And this f of x equals a times the quantity 1 plus r to the power of x. We're going to rewrite it in that form if it's not already there. Or if that would be helpful for you. Then we're going to write the initial amount, identify the initial amount, the rate of change, the growth factor. Notice our rate of change is r, our growth factor is b, and we're going to state the type. Is it growth or decay? Okay, state whether the function models exponential growth or exponential decay. All right, so the first one, do we need to rewrite it? I mean, we could put it in f of x, but we already have the a times the quantity 1 plus r to the power of x form. So we wouldn't have to do that. So what is our initial amount? Remember, our initial amount is the a. I don't know why I didn't put that in there. So here our initial amount is 10. What is our rate of change? Good, it's the 0.5. All right, how about our growth factor? Our growth factor is that whole b, if you recall, right? So that is the quantity 1 plus r is that. So this growth factor here is 1.5. So then type, is this growth or decay? Well, if this is a positive number, if it's a positive number, then it's going to be growth. If it's a negative number, it's going to be decay. So this is a growth, as exponential growth. All right, for the next one, we're going to look at it. So it is already in this form as well. The f, we have f of t, and then we have our a times the quantity 1 plus r to the power of x. So we're set here. We don't need to rewrite. All right, so knowing that, what's our initial amount? Our a. Good, is 45. All right, what's our rate of change? R. Good, it's 0.25. Did you catch, though, that it's negative, right? Because this is minus. So this is negative 0.25. Good. So what's our growth factor? Growth factor, remember, is the 1 plus r. So what is 1 minus 0.25? Excellent, 0.75. And because this is a negative, it's subtraction here, or we call it a negative here, then this is a decay. It's modeling exponential decay. Okay, this one we have y equals 2,000 times the quantity 1/2 to the power of x. So this one is not written in this form. So that's one we could rewrite. So it's 2,000 times the quantity 1 plus. Okay, so here's the thing. 1 plus r has to equal 1/2 because that's what we've got in there for our b, right? This is more the ab to the power of x form. So 1 plus what number equals 1/2? Well, this is a negative 1/2, right? So 1 minus 1/2 would equal 1/2. So then we would need to change this to be 1 minus 1/2 to the power of x. Okay, now that we've done that, what is our initial amount? Good, it's 2,000. All right, what is our rate of change? Excellent, it's negative 1/2. What's our growth factor? Good, that's 1/2. That's what we were given initially, was just the growth factor. And is this growth or decay? Perfect, it's decay because it has a negative rate of change. Awesome. Okay, let's look at this last one. We've got f of d equals 3 to the power of d. All right, so if we rewrite this, because it's in that a times b to the power of x form, so we do want to write it. So we don't have an a. We don't have a constant or a coefficient in front of that 3. So it's just going to be there. We're going to take the quantity 1 plus what? Because remember, we have to have 1 plus r equal the 3 that we've got. So r has to be 2. So 1 plus r to the power of d. Excellent. So what is our initial amount here? There's no a written. We know that it's 1. Okay, what's our rate of change? Perfect. It's a 2. What's our growth factor? Growth factor is what we were given, right? It was the 3, or the 1 plus 2 equals 3. And is this modeling exponential growth or decay? We have a positive rate of change, so it is growth. Very nice. All right, let's keep going. All right, next up with example 3. Okay, we have beginning with a population of approximately 2 million people, Nevada was the fastest growing state from 2000 to 2010. With an average annual increase of 3.2%. So in example A here, we want to write an exponential function modeling Nevada's population growth in millions of people. Okay, so first of all, we know that it's we want to use that same formula that we've been using, right? The f of x equals a times the quantity 1 plus r to the power of x. Okay, so we're using that. And we want to know what all those parts are. But here, we're going to change some things up because we're talking about population over time, right? Over years. So we're going to change this from f of x to p of t. That might be helpful for us to think about. Okay, but the rest of it, so the a is going to stay, the 1 plus r is going to stay. The only other thing that changes is our t, right? Because it was a function of x, and x was our exponent. Now it's a function of the population of time. So the population over time. So we're changing it to that. So we need to identify an a, an r, or a t. We have to identify at least 2 of those variables. Okay, if not all 3 of them. So generally the ones we're going to do are a and r. Okay, because we want to model it over a certain amount of time, and we can adjust that. So do we have an A, an initial amount, or an initial population? Yeah, it was beginning, right? That means initial population of 2 million people. So our A is going to equal 2 million. And I'm putting this in parentheses because it is 2 million, but notice we're leaving it in millions of people. So we're just going to say 2, and then the million is known. How about, do we know an R? Okay, an R is that rate of growth, or that percent. Yeah, we know it's an annual increase of 3.2%. So the increase tells us it's positive, and 3.2% we need to convert into decimal form. So that's going to be 0.032. All right, now that we have these things, we've pulled them out of our problem, we're going to put them into our formula that we came up with. So this is going to be the population as a function of time equals 2, that's our A, times 1 plus our R, so 0.032 to the power of t. Now for B, we're going to use that function to determine Nevada's 2010 population to the nearest 100,000. Okay, so we're using it to determine a population. So this is why we didn't have a t earlier. Now we do have a t, okay, because we started in 2000 and we're going to 2010. So how many years is that? Well, that's 10 years. So that is our t value. We're going to plug that into our formula. So we're going to solve for p of t is going to equal 2 times 1. I'm going to go ahead and say 0.032. I'm going to go ahead and do that addition to the power of 10. All right, and when we do that, we get 2.7. Don't forget that that means million. So this is approximately 2.7 million, or 2,700,000. Okay, I should put that. So those of you that don't remember, this is called engineering notation, right? 2.7 million, which is the same thing as 2,700,000. So if you left it as 2.7 million, I would take it. All right, then I need to move down a little bit. So let me erase. To do C, determine the average annual percent increase in population during the 1990s if Nevada's 1990 population was 1.2 million. Pardon me. Okay, so this one we're going to have to do some working backwards. Okay, so we had this P of T equals 2 times 1 plus 0.032 to the power of T. But that was when our initial population was 2 million. Okay, so now we're saying determine the average annual percent increase in population during the 1990s if Nevada's 1990 population was 1.2 million. So now my initial population, okay, is the 1.2 million. Okay, so that's going to be different, which means, okay, since this is my initial population, that 2 million that we started with up at the beginning, like up there, is going to be our P of T is that 2 million. Okay, because, let me see, because this is our 1990 population, and this is our 2000 population. So hopefully that makes sense, that this is what we started with, and this is what we ended with in 2000. So we're kind of working backwards. The time period between 1990 and 2000 is 10 years. So that equals our T. Okay, and so now the only thing left is our R, which this tells us determine the average annual percent increase. Well, if it's a percent, that's our R, and we don't know it. That's what we're actually looking for. So if we put all these things together, okay, for our equation, our P of T equals, maybe I should put it over here, P of T is equal to 2. Our A is 1.2 this time, times 1 plus R to the power of 10. All right. So we need to solve for our R. So we're going to divide by 1.2. And that gives us just 2 divided by 1.2 equals the quantity 1 plus R to the power of 10. Okay, so now the only way here to isolate the R, since it's raised to the power of 10, is to take the 10th root of that, right? Like, oh my goodness, that's a big number. So we're going to take the 10th root on both sides. Okay, so hopefully you have your calculator so you could put in what is the 10th root of 2 divided by 1.2, and you'll get 1.05. So I'm coming over this way. So 1.05 equals 1 plus R, because our 10th root and our power of 10 cancel. And then we're going to subtract 1. So then we get 0.05 equals R. And I guess I estimated, I rounded, this should have been 1.052 if I was being a little more specific there. Sorry about that. So then if 0.052 equals R, then that is also 5.2%. And that's what we would like to see. Is it written as a percent? Because they're asking for the average annual percent increase. Okay, great. Let's look at example 4. After Nevada's silver rush, its population fell from 60,000 in 1880 to 47,000 in 1890. Use an exponential decay function. So it's the same thing, but exponential decay is the same. It's just subtraction. To determine the average annual percent decrease in population during those years. Okay. So remember, we're still using that base formula. So we're calling it P of t again. It's going to equal A times the quantity 1 plus R to the power of t. So let's identify some parts there. After Nevada's silver rush, its population fell. So it fell from 60,000 in 1880 to 47,000. Okay, so 60,000 is going to be our A. That's our initial value. 47,000 is going to be the new population amount. And we need to consider the years. Okay, what is our time? From 1880 to 1890 is how many years? Good, it's 10. So this is 10 years. So we're going to plug those into our formula. Okay, so our P of t, we said was 47,000. Our initial population, A, is 60,000. 1 plus R, we don't know. And our population, or our t, is 10 years. So we're going to go about solving this the same way we just did the last one. We would divide by 60,000 on both sides. Okay, then that would give me 0.783 is equal to the quantity 1 plus R to the power of 10. I find the 10th root of that. Okay, then I get 0.975876. And you know, the longer you write this out, the more precise you're going to be. So I wrote out more digits this R. Equals 1 plus R. You subtract 1 from both sides, and we're going to get negative 0.024 equals our R, which is equal to negative, remember moving your decimal over, 2.4%. So the rate of decrease is 2.4%, okay, or population exponential decay. B, if we're assuming the population continued to decrease at that rate, estimate Nevada's population in 1900 to the nearest 100,000. Okay, so we're saying that this rate is continuing and staying steady, and we want to go to 1900. Well, we left off at 1890, so 1890 to 1900 is another 10 years. So that's our T is 10. Okay, so our R is going to stay at negative 2.4% or negative 0.024. Our T is 10, and our initial population this time is going to be that 1890 population, right? Because we're going from 1890 to 1900. So that initial population this time is 47,000. Okay. All right. So if we're writing this formula, we're going to have P of t, which is 10 this time, so P of 10, equals our initial population is 47,000 times the quantity 1 plus R. Our R is minus the negative 0.024 to the power of 10. Okay, so our population, the function of our population for 10 years, is equal to, the glorious thing about this is you can put all of that in your calculator, right? And get out your answer, which is 36,863.45. And we're supposed to round to the nearest 100,000. So P of 10 is going to be 37 37,000 people. 37,000 people. All right.